Hello, so this video is for Chem 102. We're going to be doing sections 10.5 to 10.6. And we're going to start the video with a little bit of practice. So I want you to think about this question with regards to what we talked about in class. See how far you can get. So just pause the video and just see what you can do with it. All right, so hopefully you paused the video and you tried it. Pay attention to the units here. So what I like to do first is just give out all the information that I have. I know the mass of water, the specific heat of water, the temperature change of water. I know that water and the pellet are opposite in their Q values because one is endothermic and one is exothermic. I know the mass of the pellet, the temperature change of the pellet. I'm asked to find the heat capacity of the pellet in joules per degree C. Notice that it's not asking me for specific heat in grams, so I may or may not need to use that information. We don't always have to use every bit of information that we're given. So here's how I would solve it. I would find the Q of the water because I have all the information for that. I'm using the formula S and M and delta T. And then I know that these two are the same thing but opposite signs. So the Q of the water is positive because the temperature went up. So the Q of the pellet must be negative. So I can just plug that in here, and then I don't have to use mass because what I'm looking for is joules per degree C, so I only need joules and the temperatures. The heat and the temperature is all that I need. And so I won't need that mass. So hopefully if you have any questions, you will text me or let me know, but that hopefully you can understand that problem after what we did in class. When we're talking about calorimetry, there's another type of calorimetry. We did constant pressure earlier, but you can actually just use constant volume. Or use a bomb calorimeter. A bomb calorimeter would have something like a combustion reaction, like some sort of carbon, hydrogen, something, and then they funnel oxygen in through some sort of tube or something to have reactants here. We have an ignition wire that will light it like a match and it'll burn. The heat will come out of the bomb area and into this water that we're stirring around. We're measuring the temperature increase through there, but everything is insulated. So we call this an isolated system because no heat is escaping. We're collecting information on all that heat. And again, so the Q of the calorimeter is really the surroundings, is opposite of the Q of the reaction. Same thing, except now we're talking about the calorimeter instead of just the surroundings in general. So to calculate the Q of the calorimeter, we use the heat capacity of the calorimeter. So usually we're talking about heat capacity of water, right? Because we're using water, but maybe the calorimeter is not using water. There are different ways to do this. So whatever your heat capacity of your calorimeter is going to help you decide the heat gained by the calorimeter based on its temperature change. And of course, the Q of the reaction is opposite of the calorimeter, so Q of the reaction is opposite, and you just plug in Q of the calorimeter to get that equation there. So why don't you try it? So we have a Famous Amos bite-sized chocolate chip cookie. It gives you the mass, gives you the heat capacity of the calorimeter. We know how much the temperature goes up, but we want to know the energy content in kilojoules per gram. So use the units to help you here. All right, so hopefully you paused that and you've tried it. So we're going to use this formula and plug in our capacity of the calorimeter, our temperature change. So we get a Q of the reaction. Remember, the temperature change went up, so the reaction must be negative because it's opposite of whatever the temperature change, whatever we see there. And we get our kilojoules here because they gave us the capacity in kilojoules. And if we want kilojoules per gram, well, we just take kilojoules and divide it by grams. So it doesn't have to be that complicated. You don't always have to have a formula to plug in. If you know the units you want, let the units guide you. We can check this by saying 21.5 kilojoules per gram. And we say, well, they tell me how many calories are in a serving and how many grams are in a serving. So let's see if that matches my data. So if I start with what I found in the previous section, kilojoules per gram, and then they made a mistake here. It's big C calorie equals kilojoules because little c calorie equals joules. So big C calorie or kilocalorie equals kilojoules. That's a big C there. And so here we get our kilojoules cancel, our grams cancel, and we get calories per serving, and it's 150, which is what they say on the container, which is what we got in our experiment. Next, we're going to talk about a couple ways to use changes in enthalpy or enthalpy of reaction. So Hess's law is a law that says that if we have multiple reactions that lead us when we add, imagine like adding them up to a new reaction, we can do the same thing to the enthalpies, which is really helpful because what if the reaction on the bottom we're trying to get, which is the combustion reaction for methane, but with water as a vapor, is actually really hard to measure. But I can measure the reaction with water as a liquid, and I can measure the amount of energy I need to change liquid water to water vapor. I can add these two reactions up to get this reaction because the 2H2O will cancel out and it will give me this reaction, right? That means I can also add up their enthalpies of reaction, or the enthalpy of the vaporization in this case, and I will get the enthalpy of the one I want. And it doesn't matter how I go about doing that because enthalpy is a state function. It doesn't matter how we get to the end, it just matters that we get there. So essentially, I want to go from this line to this line. And I can't really just go straight down because maybe that's really a hard path to take. So instead, I can go to this reaction, and then I can go to this reaction, right? And I wind up getting to the same place without taking that route. Hopefully that makes a little bit of sense. It's gonna make more sense when we try it. So here are some rules for using Hess's law. We're gonna change the thermochemical equation. So in the example I just gave, we didn't have to change anything, but I'm gonna do an example with you where we do change something. We're gonna change the thermochemical equations in order to get the equation that we want. Sometimes we're gonna have to make note of the physical states because those actually matter. We might have to multiply an equation by a factor. If we do that, we have to multiply the enthalpy also by that same factor. So if I have to double an equation to get something, then I also double the enthalpy of that equation. If I need to reverse an equation, let's say like I have reactants on one side and products on this side, but in the end of the reaction I want, it's flipped, well, then I would reverse the equation, and then I would change the sign, but not the number of the enthalpy. Because if my forward reaction is exothermic, the reverse would be endothermic, but it would just be the same number. And then after we've manipulated everything and we're like, hey, I think I can add this up and get the equation I want, we're going to add the enthalpy changes for each step. Let's try it. So here's what the textbook gives. I'm going to take it into another slide where I kind of organize it the way I like to do it and show you this in a little more organized way. So here are the reactions that we can measure or that we have measurements for. And here's the reaction we want to know. So the goal is to get the enthalpy for this bottom reaction. But I can't measure that one directly. So the first thing I'm going to do is I'm going to see, is everything in my reaction down here on the right side? Now, what I tried to do, maybe unsuccessfully, but what I tried to do is I tried to line up my arrows, my yield signs, my reactants and products to be on the same side. And actually, I should put this down here like this so that it matches. You can really see that. They didn't do it in the slide. They kind of just have it written over. So if I were you, if I were writing this out, I would line up those arrows. It's just going to help you visually see left side, right side, reactants, products. So let's give a quick check. For our nitrogen monoxide gas, it needs to be on the left side, and it's already on the left side. And I need one of them, and I have one of them. So that one's good. For the oxygen, the single oxygen, I have it, but it is over here on the right side. So in order to make this work, I need to flip this equation. We'll just do it step at a time. So I'm going to flip the equation. So I'm going to get the oxygen on the left side where I want it, and then the other thing, the O2, is going to be on the right side. When I flip it, I also want to cross out the old one so I don't accidentally add it up later. And then remember, if we have to flip the equation, we also have to flip the sign of the enthalpy. What I like to do is just rewrite it with its flipped sign. and then cross through the old one. I don't want to like erase it because I like to see what the old one was in case I need to backtrack. So the reason I flipped this is because I saw the thing I needed, the single oxygen was on the left side and here it was on the right side. So I got to change it to the single oxygen on the left side. So when I add these equations up, I can get this bottom equation as a result. So if you have any questions about what I did or why I did that, please let me know. I give my oxygens little loop-de-loops so we can tell they're not zeros there. Also, for this one, I have only one of these oxygens here, but I have two of them here. So what I can do is manipulate. So I have one oxygen here and I have two of them. So I can make that look a little more like a 1. So I need to change this to a 1. Now I can multiply. I guess I can technically divide, but I like to think about multiplying by a factor. So to get 2 to 1, I multiply it by 1/2. But I have to do that to the whole equation because I can't just do it to one side. So that will give me 1 oxygen, single oxygen, and 1/2 of the regular diatomic oxygen. And if I had to half the reaction, I also have to half, I must have the enthalpy. So I'll take that 498 divided by 2, and I have negative 249. And again, I like to write out step by step what I'm doing, and if I change something, I write the total new thing and cross out the old thing. All right, so now we have what we want. We want 1 oxygen on the left side. I want 1 NO on the left side, and I got those things now. Let me highlight this in green. Now we got what we want. Next is the NO2. So I have my NO2. I need that to be on the right side. And I look up here and I have it already on the right side and I need one of them and I have one of them. So that's not going to be a problem. That's already on the right side. However, look at all this extra stuff I have. I have O3s and O2s. I got to get rid of all those. So let's think about how we're going to get rid of this O3. First of all, the O3 right now is on the left side, both of them. So if I were to just like add all these up, I would have 2 O3s at the end, at the bottom. I don't want that. So I need to get rid of this O3, but I don't want to flip this one because this one is in the right place. So I'm going to flip the second reaction. So we're going to flip this one to get 3/2 O2 and O3. And then if I flip the reaction, don't forget to deal with the enthalpy change right then, because if you forget to do it now, you'll forget to do it totally. And I actually don't just leave it 142. I'm going to put plus because I don't want to get confused. Is it plus or minus? All right, so now I can cancel out my O3s because they're on the opposite side, left and right. For O2s, I have 3/2 on this side, and I have 1 plus 1/2. So 1 plus 1/2, think about this as 2 out of 2, right? So if I add this up total, so I have 3202 total on the right side. Let me write that in black so that I can cancel it out in red. So add up what you have if you have something in multiple places. Oops, that's not what I wanted to do. So this 1 plus 1/2 is 3/2. So now I have 3/2 on the right side and 3/2 on the left side. So now all the O2s are going to cancel by default. I hope that makes sense what I just did. Kind of added it up and canceled it out. If you have, 1, 2, 3, 4 of something, and then you have 4 of something that they will cancel out, if that makes sense. So now we can add up all of this. So I have the NO, I didn't cancel out. I canceled out the O3. I canceled out the O2. I canceled out the O2. I didn't cancel out this one, so that goes down. I didn't cancel out the NO2. I canceled out the O2s, these O2s. This is all canceled. Everything else is canceled. So what do I have at the end of the day? the equation that I want. So now I'm going to add up all of the enthalpies that I did not cross out. So we're just going to add them all up. So we got the negative 200.8 plus 142.7 plus the negative 249. And we should get an enthalpy of negative 592.5 kilojoules per mole for this reaction. So here's how the textbook broke it down. You can definitely read through this if you, so they kind of do they do 2 steps and then they consolidate. So you can do that too. You can do 1 step and then consolidate, and then another step and then consolidate. I kind of like to just make a little bit of a mess of it, but make sure I'm very clear about marking things out, crossing things out, rewriting things, and do it all kind of at once. But if you need to do it step by step, and then add them up step by step, and then use that. So they're doing a bunch of work, I think, because they're doing 2 equations, getting an answer, and then they're going to use this one that they made in the next part. And, oh wait, we got a totally different answer than what they got. Let's see. 142, negative 249. Okay, so I got the same numbers they have here. Maybe I just added them up wrong. I'm not in class where you can tell me if I'm right or wrong. How did they get 307? 142.7 minus 200.8 minus 249. Oh, I got negative 307. I typed that in my calculator way wrong. So hopefully you were telling me in the screen that I was typing something in wrong. That was weird. 307.1. There we go. Yeah, that's strange. I don't, because I added them all up, but I added the negative. I'm using my phone calculator, so that's probably the culprit. So use your actual scientific calculator there. If you have questions about this, let me know. Try to treat it like a puzzle and see, but you got to write stuff down. You can't do it in your head unless you're like got a photographic memory. All right, last thing we're going to talk about in this video is standard enthalpies of formation. So one way to find the enthalpy of a reaction is to do Hess's law with other reactions. Another way to find the enthalpy of a reaction is to know how much energy does it take to form each of the things in your reaction, and then we can add those numbers up or subtract those numbers to get the total enthalpy of the reaction. So standard enthalpy of formation, which is delta H with this little knot here, this means standard. So if you ever see that, it means standard. It's defined as the heat change when, and this is what makes it standard. 1 mole of a compound is formed from its elements in their standard state. So that's what makes it standard. You can have an enthalpy of formation, but it's only an enthalpy of formation, standard enthalpy of formation, if it's 1 mole of products that comes from the elements as they naturally exist. Carbon exists naturally as graphite, which is what's in your pencil lead. Oxygen exists naturally as a diatomic gas, and this is 1 mole of products. If this were 2 CO2, this wouldn't be enthalpy of formation reaction. You need to be able to identify if a reaction is an enthalpy of formation reaction, and it has to have these things that were checked off. So in order to make CO2 from its natural elements, it's an exothermic process. And this is how much energy you get when you make CO2 from its natural elements. So that superscripted degree sign shows that the standard conditions, so standard conditions are 1 atm pressure and 1 molar concentration for solutions. If we have any sort of aqueous thing, it have to be at 1 molar. If we have gases, they got to be at 1 atm in order for this math to work. And the F is for formation. The formation of an element already in its stable form is 0 because you don't have to put any energy in or get any energy out to form it. It already is formed and it's in its standard condition. And then the delta H formation for many substances is in Appendix 2 of the textbook if you need to look that up, which you probably will for some of the homeworks. So what we can do is we can find the enthalpy of a reaction, and again, it's standard under those standard conditions, same conditions as before, by looking at the enthalpy of formation of the reactants and the products. Now, you can use these formulas if you want. I'm going to show you how not to use the formula and just understand what you're doing. But if you're a formula person, you like to memorize formulas, like to use formulas, go for it. So it's going to be the sum of the moles of the products times their enthalpies of formation for the products minus the sum of the why do we have M here? I guess it moles, not mass. It should be moles. So this is going to be moles. This is also moles. So I'm not sure why that's an M of the reactants. Basically, we're taking the coefficient times the enthalpy of formation of that thing, and we're adding it to the coefficient times the enthalpy of formation of that thing for the products, and then we're subtracting the same thing, but for the reactants. Oh, and they're the coefficients. They're the number of moles in the reaction. So we're going to find the standard enthalpy of formation for this. They give us the values here, so let me just kind of copy. I'm going to show you how I would solve this. Show you how I would solve it without using the formula. Okay. So they tell me the delta H value. So this one is for Ag plus, this one is for Cl minus, and this one is for AgCl. So if it's a product, we are forming a product. So don't change the sign of the enthalpy of formation, because that's how much energy you get or you got to put in to form that thing. And that's exactly what we're doing in the reaction, is we're forming that thing. So in our math, we're going to take, so enthalpy of the reaction is going to be, you can start with reactants, you can start with products. Let me just kind of explain the reactants, and then you can kind of think about how you want to do it. So for reactants, you are unforming reactants. So we're doing the opposite of forming them. So we have to change the sign of the enthalpy of formation, because we need to find the enthalpy of unformation, which would be the opposite. Does that make sense? And then once you have all those signs, you're just going to add them all up. So let's do it. So we start with our reactants. Ag plus, this is a reactant, so I need to change the sign. So I'm going to say negative 105.9. Cl minus, that's a reactant, so I got to change the sign. So I'm going to say plus positive, and I know that it's silly to say plus positive, but let's just keep them all together. And then AgCl, we don't want to change the sign because we're forming that product. So negative 127.0. And then we just add them all up. Or you can plug into the formula that I just showed in the previous page. Feel free to do that. So 167.2 minus 105.9 minus 127. Nope, type that in wrong. Don't use your cell phone or a calculator, kids. Minus 127. I get negative 65.7 kilojoules per mole here. Now, if they had coefficients, like if there was a 2 here, I would multiply this by 2. But there weren't coefficients in this example, so we don't have to worry about them here. So let's make sure we get the same thing they got. Yeah, 65.4, 65.7. They, 5 know why we would have gotten separate. 167, 105. Oh, I used 105 point. So they wrote 105.6 here, but then wrote 105.9 there. That's why it's different. Here, the kind of is confusing because you're like, oh, like I'm using the number as is, but I'm flipping that sign. So we're subtracting. So that means that we change this sign, um, and we change this sign because you're bringing that subtraction through. And if that's confusing to you, just do what I did. All right. So calculate the standard enthalpy of formation of acetylene from its constituent elements. So we're going to combine the two things, enthalpy of formation and Hess's law for this. Let me see. That's it. Yeah. What I want you to do is work this out, and we can we'll definitely go over this in class. It's our probably first example of the day. Just want to make sure that you get this. So try it and then bring it to class and we'll go over it in class.